Yeah, hi. In this video, we continue with project scheduling, but now we talk about cost considerations. So if you think about the cost categories here, it's going to be direct cost, labor, material to undertake an activity, and so on. Indirect cost, like the overheads, uh, and opportunity costs. There will be penalties if the project is delayed. There will be bonuses if the project is completed ahead of schedule. So this is a typical relationship between them. Direct cost goes down as the duration of the project is up. Indirect cost goes up, and the opportunity goes up if the duration of the an activity is delayed beyond a reasonable amount of time. So the objective here is to select the optimal project duration to minimize total cost, which is the sum of the direct, indirect, and the opportunity costs. Okay. So the method we're going to use is called the CPM method. It's called critical path method, crashing procedure. And what we want here is this is a deterministic approach. So we go back and assume that activities durations are known in advance. There is no probability distribution associated with them. Okay. So activities are known with certainty. We assume that activity time only depends on the amount of money allocated to the activity, so that we can control the duration of the activity by how much money we spend on it. Uh, Two crucial time points for each activity. We assume that there's normal completion time, call it NT, at normal cost, call it NC, and there's a crash completion time, call it CT, for a crash cost. Spending money beyond CC will not reduce completion time further, so we don't go beyond that. Crashing means reducing an activity's completion time by committing additional money or monetary resources to it. We also have, so we need an assumption to do this because suppose you have an activity which takes say 10 days and you can reduce it by 5. So maybe the first day of reduction cost you $5, but the last day of reduction can cost you $10. We're gonna say this is not the case. So any day, whether it's the first day or the last day of reduction, it costs the same amount of time. So we call that the linearity assumption. So if any amount between the normal cost and crash cost is spent to complete an activity, the percentage decrease in the activity's completion time from its normal time to crash time equals the percentage increase in cost from normal cost to crash cost. Exactly, the linearity assumption. So if I take normal time minus crash time, that's my maximum possible time reduction. Okay? And if I take the crash cost minus the normal cost, that's the maximum possible cost required to achieve maximum reduction time. So my M is C over T. So I'm ignoring the sign because one of them goes up, the other one goes down. Is the marginal cost of reducing an activity's completion time by 1 unit, which is this is the slope. Okay? So the rationale for this is the crashing procedure focusing on focuses on minimizing the direct cost associated with a target project completion time. So I want to spend money on reducing the activity durations in order to achieve a minimum duration activity. So what would be the idea is to pick those activities with minimal marginal cost because these are the ones cost the least to reduce the project duration. But the problem is I cannot pick all of those because if I pick one, then that will change. Once I reduce one activity by 1 day, that's going to change the dynamics of my project. Some of the critical activities may become non-critical. and so reducing them, even if they had minimal marginal cost, will not reduce the project duration. So that becomes an issue. And you can see we cannot do that. So wishing to shorten the duration of the overall project, well, maybe let's do one activity at a time. So compress the most promising activity, critical activity, with the least marginal cost by 1 day. But then at that point, you have to solve the whole project, redetermine uh, the duration, and then pick the next activity with the lowest marginal cost and reduce it by 1 day, and so on. So that's going to be really a very tedious process. Uh, what you have here is the details of what I've just described and the definitions. MI is the marginal cost. They're just giving you the details what we had up there. And graphically, this is my normal time. This is my this is my normal time. This is how long an activity takes. If I crash it, it takes less. So this is my crash time. This is my normal cost associated with this, and this is my crash cost associated with this time. And this is my line, and that's the slope of this line is my marginal cost. Okay, and T is the maximum possible crash time. So as critical activities are crashed, other activities will become critical. So makes it very difficult to identify the sequence of activities to be crashed in order to reach a project's all crash time while minimizing direct cost. So the approach, fortunately, we can do this with linear programming. So if we can formulate this problem as a linear program, we can do that, right? And so let's do this linear, apply this linear programming method on the example we had. Okay. So in this case, this is my same problem. So I'm given the activities. I have the precedence relationships. That's their normal time, which is now the early, and we said the duration of each activity. We call it the normal activity or normal time 137,491. This is the crash time. So activity 1 cannot be crashed in this model. Activity 2 can be crashed to 2 days. C can be crashed to 3 days. D can be crashed to 2 days. 9 can be crashed to 6, and the last one cannot be crashed. So the maximum amount I can crash each activity is 0, 1, 3, 2, 3, and 0. I'm also given the costs. So undertaking activity A cost me $5. Activity B cost me $5 and it takes 3 days. Activity C cost me $11 for the 7 days. Activity C cost me $8.50, and 5. And this is the crash cost. So if I crash activity B to 2 days, it's going to cost me $12. And so that extra day is going to cost me $7. So this minus this divided by this, so it's going to be 7. That's my marginal cost per day. And activity C, if I crash it completely by 3 days, it's going to cost me $17, which means 17 minus 11 over 3 is $2 per day reduction. And the same thing here. So this is $12.50 if I reduce it from 4 to 2, which means it's $2 per day. Again, this minus this over this. And this the crash cost here is $16.50 minus the normal cost over 3 gives me $2.67, and the last one cannot be crashed. Okay. So I can see here that my normal cost for this project is $43, and I can do it in 14 days. If I crash each activity to the fullest, it would cost me $68. And how long is it going to take me to do the project? So I need to identify the critical path for these crash times. Let's do that. Oh, first, this is my normal project. the one we've seen before, would cost me $43. So if this is the project with the crash time 1, 2, 4, 2, 6, and 1. And so these are critical. This is critical activity. This is critical activity. This is critical activity because their slacks are zeros. So this would be a critical path. 1 plus 2, 3 plus 6, 9 plus 1, 10. So the all crash time would be 10, and we know the crash cost is $68. I still have a slack of 2 here, so that's not on the critical path. So the question is, since I know that I can complete the project in 10 days, the question, can I complete the project in 10 days for less than $68? Because here I crashed all activities to the maximum, maybe I didn't need to do that to achieve the 10 days. So how do we do that? The answer is we can do it with linear programming. Okay, so we're going to model this as a linear program. So we go here. So this is the linear programming formulation for the crashing. In this problem, we're going to identify two sets of decision variables. One related to earliest finish time, because once we crash an activity, its earliest finish time is going to change, and that's going to change earliest finish time of subsequent activities. And the other one is going to be the crash times, the amount of crashing, how much we're going to crash each activity. So these are the ones, the decision variables. Their values will help us determine how much to crash each activity. Okay, and then we can compute can go back and solve the project the way we did before and end up with a critical path with a minimal cost. So let's define those decision variables: XA, XB, XC, XD, E, and F, the earliest finish time for all these activities, and Y. Let's define another set of variables called Y, B, C, D, and E. Amount of time activities B, C, D, and E are crashed. I didn't need in this example YA, YF, but I could use them if they were crashed. Okay. So now the objective is to minimize the incremental total direct cost associated with crashing to reach the target project duration. So I want to minimize Z, so this is the marginal cost, incremental cost, so $7 for activity, the marginal cost, the M for activity B times how many days I want to crash activity B, 2YC, 2YD, and 2.67YE. And I'm going to have 12 constraints divided into 3 families. First set of constraints, the most involved, so you need to pay attention here to follow this. So in this case, I want to ensure that each activity's earliest finish time X is not smaller. It's at least as large as the sum of its earliest start time plus its activity time after crashing, after adjusting for crashing. That is, I want Xi to be greater than the start time of I plus the normal time of I minus the crash time of I. The problem with this is the start time of I now is going to be adjusted because earlier activities they may have crashed, and the start time of I is not what the known start time of I that I had before. So where ESTI is going to be, we're going to define it as the maximum of the XI's of its immediate preceding activities. Okay, so that's the maximum of XI's. XI's are the earliest finish times of all preceding activities. Okay, so let's look at our constraints. The first one, so I need XA to be greater or equal to start time of A plus the normal time of A minus the crash time of A. which now all my constraints would follow this pattern, but this looks like an awkward pattern. So the start time of A is 0, the normal time is 1, the crash time we know is 0, so that gives me XA greater or equal to 1. So that's my first constraint. We should put it in this format. The second one is the XB greater or equal to ES start time of B plus the normal time of B minus the crash time of B, or the amount of crashing of B that I want to decide on. So that's a decision variable. So XB now is greater or equal to the earliest finish time of preceding activities that lead to it. That's only one. There's XA. So instead of STB plus, that's 3 minus YB. So we want to rearrange this to make it look like a linear inequality. So we take XA here, we take YB here, and that's going to be greater or equal to 3. So that's my second constraint. And same thing for C, just did exactly the same thing for C, exactly the same thing for D, and exactly the same thing for E. So let's do E here. XE, EST of E, and T of E minus Y of E, so that's going to be XE, and the one that leads to E is B, so that's going to be XE greater or equal to XB. Normal time is 9 minus YE, which is a decision variable. Take this here, take this there, it becomes negative, that negative becomes positive, and 9, keep it on the right hand side, so I end up with this constraint. Okay, now for F, so I have XF is greater or equal to EST of F and TF minus YF. So what should I replace this with? Oh, because I have two nodes that lead to F, D, and E. So I need to repeat this twice now. So I replace this by D, and I repeat exactly the same thing, and I replace it by E. So that way, that's the way I can get XF to be larger than the maximum of these two. Okay, so we got XF minus XD, and the normal time is 1 minus YF. I cannot crash it at 0. So I take this to this side, and I get this constraint. And the same thing here, just now instead of D, I take E, because also E leads to F, and I got this constraint. Okay, so that's my first set. Then I want also to make sure that each of the activities is not crashed beyond its minimal. So now I want YB to be less or equal to 1, YC less or equal to 3. That's the maximum I can crash activity C, YD less or equal to 2, and YE less or equal to 3. So that's an easy set of constraints. And the last one is I want to make sure that I reach my earliest finish time. So I want XF to be equal to 10, and I can write that as a constraint. Okay, and so put all of these together, run it as in Excel as a linear program, and then I will get my values for Y, YA, YB, YC, YD, YEF, and then that would determine for me the minimal cost for the minimal cost to achieve the 10-day duration for this project. Okay, thank you and take care.